All right. Thank you, thank you. I will begin with a word of prayer. Oh, sorry. Dear Heavenly Father, we thank you for this day. Again, I thank you for this class, this opportunity we have to meet and study your creation together. Help us to glorify you, what we do, and just understand a little bit more about proof by mathematical induction today, Lord. In your name I pray, Lord Jesus. Amen. All right, so let's get back into it. So my next example for induction requires a definition, right? So this is another example of a recursive definition. And so at least the first story arc of class, I'm going to be talking about finite sums, which is something you could easily take for granted, but I think this is a nice laboratory to sort of test basic induction proof ideas on. So here's the definition. All right, let a sub I be an element of the reals for I equals 1, 2, and so forth, all the way up to n. Then we define the sum. Well, I should say, I'll include the word recursively here. We recursively define the sum I equals 1 to n plus 1 of a sub I to be equal to a sub n plus 1 plus the summation, all right, I equals 1 to n of a sub I for each n greater than or equal to 1. Moreover, and usually people put the last part first, but I'm putting it last because I'm weird. The sum I equals 1 to 1 of a sub I is equal to what? Can you guys tell me what this should be? Help me finish this definition here. What should the sum I equals 1 to 1 of a sub I mean? 1? Almost right. A sub 1, right? So this is what we mean in that special case. So this is how we define the finite sum inductively. So just to show you how this works, for example, if we have the sum I equals 1 to 2 of a sub I, this is equal to a sub 2 plus the sum I equals 1 to 1 of a sub I, right? By the definition, by the recursive definition, and then what is that equal to? By definition, this is a sub 2 plus a sub 1, right? Again, by the definition. So this definition reproduces what you kind of expect, right? If I have the sum I equals 1 to 3, how's that go? Of a sub I, we do a sub 3, right? Plus the sum I equals 1 to 2 of a sub I by the recursive definition. But then we just work that out, right? From the step above, we know that this is what? A sub 2 plus a sub 1. So this gives us, a sub 3 plus a sub 2 plus a sub 1, all right? And so you can see, apparently, right, the sum I equals 1 to n of a sub I is equal to a sub 1 plus a sub 2 plus ... plus a sub n. All right, so this business that I'm doing right now is giving, what we're doing actually is we're giving a rigorous meaning to that plus ... That's what's happening here, right? So that plus ... is, rigorously contained in this concept. Any questions? So, like the first theorem we can prove about this proposition is that if we have the sum I equals 1 to n of a sub I plus b sub I, well, that's equal to the sum I equals 1 to n of a sub I plus the sum I equals 1 to n of b sub I, right? And also, if we have the sum I equals 1 to n of a constant times a sub I, it's equal to a constant times the sum I equals 1 to n of a sub I. Now, I'm giving all these proofs under the assumption that the a sub i's and the b sub i's are real numbers, all right? But if you study the things we're doing, the arguments would equally well apply so long as whatever we're adding, as long as there's a way of adding and scalar multiplying the things that we're looking at, these arguments should still be like legitimate, right? So let's prove, which guys want to prove 1 or 2 here? Student's choice. 1, all right, 1 it is. So the proof of 1. All right, so let the sum, well, let me avoid writing here. Let 1 be Pn, the induction claim, all right? Or if you like, the induction hypothesis. Well, we're not the induction hypothesis yet. It's the induction claim at the moment. So notice that the sum I equals 1 to 1 of a sub I plus b sub I is equal to a sub 1 plus b sub 1, right? By definition of the finite sum, right? And then, what's that? Again, by the definition of finite sum, this is the sum I equals 1 to 1 of a sub I plus the sum I equals 1 to 1 of b sub I. Thus what? Thus the induction claim, P of 1 is true, right? Because we showed that number 1 of the proposition holds in the case that n equals to 1, right? So next, what do? We assume inductively, right, or suppose inductively, Pn holds for some n in the natural numbers, all right? And then what we're going to do is we're going to look at the sum I equals 1 to what? You guys tell me. What are we trying to do? Is in proof by mathematical induction, we're trying to show that P of n implies P of n plus 1, right? So what I should look at the sum I equals 1 to n plus 1, right? So let's do that. Put n plus 1 here. What's my first step? You guys tell me. Fill in the blank for me, and I'm going to say by definition of the finite sum. What do I put here?
A sub n plus 1 plus b sub n plus 1 plus the sum I equals 1 to n of a sub I plus b sub I.
Very good. That's exactly it. That would be the right first step here. And then we're going to do a column stack proof here. So this is a sub n plus 1 plus b sub n plus 1 plus what? The sum I equals 1 to n of a sub I plus the sum I equals 1 to n of b sub I. My reasoning here is by the induction hypothesis, all right? Which I'm going to abbreviate as IH. Would you guys also like to abbreviate induction hypothesis as IH? I see some nodding. There's less letters to write, right? You guys are like, yes, less letters to write sounds nice. If you're going to give me an 8-page test, you monster. That won't happen again. I spent 12 literal hours grading your test. I'm not doing that again. I know Sprano often gives like a 7-page. Well, he gives like a 4-page test, but it's front and back. So I don't know. I was trying to obtain the Sprano length test, and I think I achieved that. But I also achieved the realization that I don't want to grade that ever again. That's a final. That's not a test, like lengthwise. I mean, well, it's a short final. But anyway, so rewriting this, So again, what I'm trying to say, if you're not hearing me, is I'm sorry the test was so long. But on the other hand, I'm not too sorry because it probably was helpful for you guys to have it that long because it gave you at least something that you could do somewhere, right? And there are people who got most of it right. The last page was come on. That's understandable. Anyway, so this is what? By algebra? I do think as a class you guys are doing really well, though. There are some people who are, further along than others, but I think everybody is making some progress towards the end. I will replace the final exam score with the for your lowest test grade, if that's helpful. And for some of you, that will almost certainly be helpful. So do not despair. Although if you did make a bad grade, maybe work harder. Let's see here. So n plus 1. And if you're already working hard, then you should despair. But I'm just kidding. No despair. But so what we have just shown is that this is what was my last step is what by what? Definition of the finite sum, right? And so then what? Thus, P of n implies P of n plus 1. Hence, 1 holds for all and in the natural numbers by proof by mathematical induction. All right. So I think this is not a bad proof. It's a pretty good proof, I think. I'm happy with it. All right. Let's look at, and this is a question. Let me look at another one here. So one of the things that I found a little bit surprising when I first saw it, and I was like, is that really true? Like, why is that true? Was the fact that you can swap finite sums. So let me just take a second to show you what it means in terms of an example. So let's talk about swapping finite sums. All right, so like if I have the sum, I'll try to keep it relatively simple. I equals 1 to 2. The sum j equals 1 to. I'll resist the urge to put 3 here and put a 2 just to keep it simple. All right. So suppose you got like I plus I squared j. All right. Okay, so if we do that, how does that work out? So we do the sum over j, what's that give us? It gives us I plus I squared, right? Plus what? Plus I plus 2I squared, right? So the first term is the j equals to 1. This over here is j equals to 2. Then, of course, we could make our life easier, do one simplifying step before I actually do the sum. This is what? This is 2i plus 3i squared, right? Which is what? So that's, I'm going to need room here. So this is 2 plus 3 plus 2 times 2 plus 3 times 4, right? So what's that? That's 6, 9, 21? 21, I think. All right, that's 21. What happens if instead of doing the sum over I and j, we do sum over j then I? The same thing being summed over. So j equals 1 to 2. The sum I equals 1 to 2. What's that look like? So put in I equals to 1, what do we get? We get 1, right, plus j. And then put I equals to 2, we get 2 plus 4j, right? This is the I equals 1 term. This is the I equals to 2 term. Let's make a simplifying step before we actually calculate this finite sum. That's the sum j equals 1 to 2 of what, 3 plus looks like a 5j, right? Which then gives me what? That gives me 3 plus 5 plus 3 plus 10, also known as 21. This is not an accident, right? This is not an accident. This is a general theorem that if you have two finite sums, you can swap their order. So let me write it out carefully. So this is my next proposition, 4.1.21. And it says the following: let a sub I and b sub ij be elements of the reals, all right, for I and j in the integers, positive integers rather. And suppose c is a real number, then for each m and n in the natural numbers, all right, number 1, the sum I equals 1 to m, the sum j equals 1 to n of b I j is equal to the sum j equals 1 to n, sum I equals 1 to m of b I j. In other words, this thing we just saw in, I guess I should have labeled that example 2, right? The thing we just saw in example 2 is in fact a general identity. All right? And yeah. And then number 2, we have that the sum I equals 1 to n, the sum j equals 1 to m of a sub I, b sub ij, all right, is equal to the sum I equals 1 to n, a sub I, times the sum j equals 1 to n of b sub ij. So what I'm saying here is that in the case of a double summation, if part of the thing you're summing over has no dependence on the summation variable, right? See this? Like this. This has, this a sub I has no j dependence, right? It's constant with respect to the sum over j. I can pull that out of the sum like this, just like property 2 that we didn't prove yet today, all right? And I probably shouldn't, because I think it's one of your homeworks. All right. So, yeah. So this is a claim. Now, I think in the interest of, well, I don't know. I'm never uncertain how much. Never certain how much time I have in here to write things out. I think I have time to write this out, so I better do that. Let's see here. Where should I prove it? So let's prove 1. How do we start? So what I would do is I would say let m be an element of the natural numbers, right? This will be fixed but arbitrary in what follows. I don't always write all that out. I'm just writing for emphasis here, guys. So we're just going to we're going to fix m. Yep.
On that red summation for the second one, sorry, is that supposed to be j?
Yes, thank you. Still in the marker. There you go. Thank you. Muchas gracias. Now, all right, so I'm going to suppose that I'm going to let m be an arbitrary integer and let p of n be 1, all right? So we're going to consider n equals to 1 to start with. So we've got the sum, I equals 1 to m of the sum j equals 1 to 1 of b ij, right? So that's what I would consider for p of 1. I put n equals to 1. I'm trying to show that this identity holds in the case n equals to 1 for fixed m, all right? So by definition here, this is what? Oops, sum I equals 1 to m of what? Of b sub 1 j. That's what the definition of the finite sum is in this context, right? But that is also equal to the sum j equals 1 to 1 of the sum I equals 1 to m of b sub I j. Did I do? I might have, just a second here. I think I may have. I gotta flip that. Flip. That's not right. Why am I? Why? It's not right. What do I need to do? I'm like, something feels off here. Yeah. Which is the one that's being summed from 1 to 1? J, right? So that means that the I is left alone, right? And we just have a 1 here for j. Yeah? And likewise, then over here, I've got some, I think this is fine. J equals 1 to 1, I equals 1 to m of b sub ij, right? So that was the wrong step there. Therefore, p of 1, true. All right. So then, assume inductively, suppose p of n true for n in the natural numbers, right? Consider, let's see here, we got to consider the sum I equals 1 to m, the sum j equals 1 to n plus 1 of bij, right? So that is going to be equal to the sum I equals 1 to m, parentheses, b sub I. I'll put a comma in here to keep it separate, okay? I comma, the comma is, you can always put a comma between indices if you want to draw attention to their distinction. It doesn't have to be there. That's just kind of a custom of mathematics. You can put a comma there if you want, but you don't have to. But at some point, your instructor will be like, what do you mean? Or your students will be like, So you try to avoid the suffering. Well, maybe some, but some suffering can't be avoided. But this is definition of what? The finite sum over j, right? It's finite sum over j, that's that one. And then what can I do? I can use the one that we already proved, which is this is the sum I equals 1 to m of b sub I comma n plus 1 plus the sum I equals 1 to m of the sum j equals 1 to n of bij, right? By 1 of the earlier proposition. Right, because we proved that the sum of the sum is the sum of the sums. That was the first thing we proved today, right? Well, first thing I proved today. You guys proved something else, I hope. And then what? So what can we do now? We've got what? The sum I equals 1 to n of Bij, right? So now I can apply the induction hypothesis to flip the summations here, right? So this is the sum j equals 1 to n. The sum I equals 1 to m of Bij by the induction hypothesis. Man, I'm really liking that induction hypothesis abbreviation. I'm liking it a lot. Maybe don't do that in a paper if you write one, but it'll work for this class. Then what? I think I probably should have been more greedy in this step if I wanted to write less, right? Because I could have taken the first sum and rewrite it as what? It's kind of the same stupid trick as the n equals 1 case, you know? Which is to say, oh, well, this is really the sum j equals 1 to n plus 1, right? This is the sum j equals n to n plus 1, I should say. I'll get it eventually here. It's the sum j equals n plus 1 to n plus 1. Oh, man. Just a second here. I'm spinning my wheels. I thought I had it, but I better be careful. Let's be careful here. So my next step was to factor out the sum over j. Did I drop a... Did I make that? I do. Oh! Oh, ho, 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 ho. I must do something sneaky here. I forgot. There is something sneaky here. Watch this. Wait, is that right? No, that's not right. I'm sorry, guys. Give me a second. I did type these notes myself, I promise. I've got the sum j equals 1 to m of n plus 1. I think I messed up. Oh, come on. Oh, this is annoying. I'm sorry, guys. We're going to have to bail on this. It's got the right idea, but my sums are all... Well, give me a second. I have done something dumb. Maybe not in the notes, but definitely in class. All right, so I've got the sum I equals 1 to n plus 1 in the proof in the notes. And I've got I equals... See, this is the thing, is I have the n and the m flipped in the notes. And... Oh... I'm sorry, guys. Let me project this, because there's no... Maybe I shouldn't teach this class. Oh no. Of course, if I'm going to rely on technology, one, two, three. Well, all right, let's fix the proof. I guess I got no choice. All right. Oh, goodness gracious. All right. I'm going to take my medicine. I will make a video correcting this proof later. Let us go on to the next thing. It's not, you don't want to, I'll burn another 30 minutes of class correcting this. We won't learn anything. Yeah.
I have a separate question about, so the notation for b sub ij, is that representing like an element of matrix?
Oh, okay, so it could be. I mean, certainly we could arrange b sub ij into a matrix. If we think of I as the row index and j as the column index, we'd be talking about like an m by n matrix. But it doesn't, I mean, that's kind of a matter of taste, you know? So like in my example 2, b sub ij would have just been I plus I squared j, you know? But the point is you've got some object that you can index by a pair of positive integers, you know? So, okay, yeah, I'm going to have the discipline not to, I mean, everything in me wants to fix this right here for you now, but I shouldn't do that. Let's go on. Let's go on. You've got to know when to hold them, you know? And at the moment I'm running, so let's move on here. The next theorem, but anyway, if I didn't accidentally switch the role of m and n, what happened in my proof today is like I inadvertently switched the m and the n in my mind when I wrote it down, which made the proof I was doing having the m and the n role interchanged. And when I do that kind of thing, I tend to do it more than one place. So when I try to correct it, I have to find all of the places where I've done it. And if I miss one of those, it's all going to fall apart again. And so having identified my weakness and not being willing to fix it in real time, I'm going to just post a video. So sorry. All right, so the next up here. So the next theorem, if, you know, I can find it. A and B are complex numbers. Then A plus B to the n power is equal to the sum k equals 0 to n of n choose k, a to the power n minus k, b to the power k. All right. Where n choose k is equal to n factorial divided by k factorial times n minus k factorial. All right. This is red n choose k for its significance in terms of combinatorics, okay? Which I won't try to elaborate on in here. All right, so this is the famed binomial theorem, all right? And we can prove this by induction, actually. I had such high hopes for projecting the end of class today. Connection error. Unable to connect to destination. You don't say. All right. All right, so this is my induction claim, right? Let's call this whole thing P of n. So so we're going to do proof is by induction. Induction on n starting at n equals to 0, right? Notice that, let's see here, 0 choose 0 is 0 factorial over 0 factorial times 0 factorial, also known as 1, okay? Because 0 factorial is 1, and 1 over 1 is 1. 1 times 1 is 1. All right, you get it. So a plus b to the 0 power is, well, the sum k equals, well, it is in fact equal to, I really should have done this one first, guys. So my bad. A plus b to the 0 power is 1. And what else? The sum k equals 0 to n, k equals 0 to 0, of 0 choose k is, my bad, goodness gracious, I can't do anything right today, n minus k, b to the k. So k equals 0 to 0, just puts k equals to 0 this, we get 0 to 0, 0 choose 0. A to the, I was supposed to put 0 here as well, eventually I'll get it, guys. 0 minus k, but k was equal to what? 0, b to the 0, which is what? This is all 1 times 1 times 1, it's 1. So my point, if I can eventually make it, is that p of 0 is true, all right? P of 0 is true. How about suppose p of n true, right? Consider a plus b to the n plus 1 power, right? Then that is equal to what? By definition, this is equal to what? We talked about this last class. I mean, we maybe use a strong word. I talked about it to myself last class, and many of you watched that video, I believe. So a plus b times a plus b to the n, right? That's the definition of exponent, which we also define recursively. Then by the induction hypothesis, this is equal to what? Right? That would be by the induction hypothesis. So then what do I do? Any ideas? How about this? We could rewrite this as like the sum k equals 0 to n of n choose k times a times that. But a times that is what? A to the n minus k plus 1 times b to the k plus the sum k equals 0 to n of n choose k, a to the n minus k, b to the what? B to the k plus 1, right? I'm using proposition 2 of the first thing I wrote today. All right? And past here, we're going to have to really think about it, right? Our goal is to make steps, right? So eventually we can go dot, 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 right? And we'll get to the sum k equals 0 to n plus 1 of what? N plus 1 choose k, a to the n plus 1 minus k times b to the k. All right? And because we can make, and I'm just arguing that we can in fact supply those dot dot dots there, it can be done. This shows that n implies n plus 1, all right? Therefore, by proof by mathematical induction, the binomial theorem is true. All right? My intention was to show you those steps with a projector, so this is the best I can do at the moment. I must go on. Obviously, these are a weighty dot, 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 right? This is a half a page of my notes, and it's not, you know, any given day I might get stuck on some of these steps. It ultimately rests, do you guys know what this, rather than continuing with my sketch of the proof, this is an example of a proof sketch. let me talk a little bit more about the binomial theorem because it is useful for us, right? So this has to do, of course, with Pascal's triangle, right? Which is what? You put 1 up here, 1, 1, 1, add the numbers above, right? Like this. So we get what? 4, 6, 4, 1. What's the next row?
1, 5, 10,
Mm-hmm.
10, 5, 1.
All right. I'll stop there. So the significance of these numbers is that they reveal the binomial coefficients. All right? Like this is 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5. So we can calculate binomial coefficients with Pascal's triangle, or if you remember this formula over here, you can just apply that directly, right? So for instance, if I had, like x squared minus 3y, and I wanted to calculate it to the 5th power, I could just write it down. X squared to the 5th power, and then plus 5 times x squared to the 4th power times minus 3y plus 10 times x squared to the 3rd power times minus 3y squared plus 10 x squared to the 4th power times minus 3y cubed plus 5 times x squared to the, oh man, look at this. That's not good. My power was decreasing. This is just how today is going. We started with this, we went to 4, we went to 3. Somehow it's climbing back up again. That's not good. That was supposed to be a 2. This one should be climbing my 0 power, 1 power, 2 power, 3 power. This is the minus 3y to the 4th power. And then finishing blow here, plus minus 3y to the 5th power. And then, of course, you could simplify the exponents there. And all of a sudden, we've calculated x squared minus 3y to the 5th power in two lines, right? I think multiplying this out is considerably harder, right? So we're looking, what, x to the 10th minus 15 x to the 8th y. I'm going to regret this. Plus 90 x to the 6th y squared minus 270 x to the 4th y cubed. What's 5 times 81?
405?
What's that, 405? 405, okay. So plus 405 x squared y to the 4th minus 243 y to the 5th. There you go. So obviously Pascal's triangle and like the binomial theorem is something you really need to know in terms of getting yourself out of a corner in certain algebra problems, right? So I wanted to make sure I shared that with you. Okay, so moving on here. The next kind of induction we should talk about, there's really two other things to talk about induction-wise. Two other ideas. The one is so-called strong induction. And number two is the so-called well-ordering principle, or the WOP. Now we will use the well-ordering principle in a significant proof we come to later, so I'll probably illustrate that in a future lecture. But these are logically equivalent. Now strong induction is a little bit different. Sometimes it's called complete induction, PCI. See if I have a good example for you guys. I guess I should define it, right? So here's the definition of strong induction. Suppose P of n is proposition defined for n in the natural numbers, then proof by complete induction or PCI, also known as strong induction, constitutes the following steps. Constitutes the following argument. I'm going to go buy myself a projector, guys. I've had it. P of 1 implies P of 2. Number 2, show P of k true for 1 less than or equal to k less than or equal to n implies P of n plus 1. And then step 3 is to conclude. I hope you guys are done with this. I'm sorry if you didn't get it. 3. We can conclude P of n true for all n in the natural numbers by PCI. All right. So what's the difference here with strong induction versus what you might call regular induction, or would people, if they're going to make a distinction, you'd call it weak induction, right? So what was the logical structure if I don't confuse M and N in my proof and actually complete the thought, for example. In the regular induction proof, we assume, first of all, the starting point, the base case, is to show that the base case is true, right? We don't show an implication, right? We don't start with P of 1 implies P of 2. We start with usually P of 1 is true. That's step number 1. That's the base case, right? And then our induction hypothesis is a little bit different here, right? The strong induction hypothesis doesn't assume just true for n, for a fixed n. Rather, for every n up to n, and including n. Or if you like, for every k equals 1 all the way up to n, right? That's a different assumption than weak induction, at least on the surface of things. So strong induction is a good tool if your argument involves like more than one level. Like if for some reason you've got something that's defined recursively in terms of not just one step, but like a couple of steps behind, then strong induction might be a better way to prove it if you're needing to assume not just the current level you're at, but like several steps before, you know? Let's see if we can prove something with strong induction. So here's my example 3. Claim if n is greater than or equal to 2, then n has a prime factor. All right. So I think you guys can see what the induction claim is going to be, right? It's with the sentence I just wrote. That's this altogether is my P of n. All right. So let's see here. So like the proof goes like this. Number 1. I guess so. My proof works with an inductive set. I guess that might be helpful. We can let. I'm going to try to reword the proof here. All right. Let me forget my notes for a second. Let's see if we can figure it out together. So how do I start if I'm going to use complete induction here? So this is, so complete induction doesn't have to start at 1. It can start somewhere else, right? So this claim doesn't start at 1, does it? This is a claim that starts at 2, right? So for here, logically speaking, like here's a play-by-play. We want to show that, P of 2 implies P of 3, right? And then we want to show that P of K true for K equals to 1, 2, n implies that P of n plus 1 true, right? That I'm not playing with a full deck today, guys. Then conclude by the principle of complete induction. All right. So this is where I think, as a student, it confused me when I saw people doing strong induction, because it seemed I didn't understand that they were proving an implication to start the strong induction. Because there's different ways of proving an implication that don't look like you're doing an implication. Like, what's a stupid way of proving P of 2 implies P of 3? Like, what if we just show that P of 2 and P of 3 are both true? Then the implication holds, right? So notice that n equals to 2 and n equals to 3 are prime, and so have a prime factor, right? Right? Any number is its own factor, because any number times itself is, any number times 1 is itself. So n equals 2 and n equals 3 is prime factor. Therefore, we've established number 1. P of 2 implies P of 3. You're like, well, you didn't show P of 2 implies P of 3. You just showed that P of 2 and P of 3 are true. Guilty is charged, but logically speaking, that follows. Yeah. All right, so assume that if K is greater than or equal to K is greater than or equal to 2, good grief, I can't. I want to sip. So if K sorry, I'm having trouble thinking of how to write it. P of K is true. Let me put it into words. Suppose every integer between 2 and n has a prime factor. All right, I've got some mental block at the moment, guys, to write it using symbols. I don't know what's wrong with me. Do you agree that's the strong induction claim? We're assuming that every integer between 2 and n has a prime factor. Now we want to consider n plus 1. I guess I should say for what? N greater than or equal to 2, right? But I think that, do I need to say that? I mean, I said between 2 and n. Doesn't that already mean that n is not before 2? I guess, fine, if n was minus 5, there are numbers between minus 5 and 2, right? Maybe I do need that, logically. All right, consider n plus 1. So there are two cases, right? Either n plus 1 is prime, right? Number 1, if n plus 1 prime, then n plus 1 has a prime factor. So we're done. So that would be to say that P of n plus 1 true, right? What's the other case? Otherwise, n plus 1 is equal to r times s for some r and s in the natural numbers, right? Either n plus 1 is prime or it's composite. To be composite means that it's a product of integers. In this context, we can easily see that they must be positive integers, right? So what does this mean? What can you tell me about r and s here? You know, how about this? N is equal to, trying to think of how to argue this. I mean, it's kind of obvious, but I'm gonna write it down. You guys give me an argument. How about that? But r and s are less than n. So we're assuming. I should say for some r and s with r and s greater than 1, right? The definition of composite, it does suppose that we have non-unit factors. That's important, right? It's not just enough that n plus 1 is equal to rs, like to complete the thought. Because I can always write, you know, pick your favorite prime, 7. 7 is 7 times 1. Does that mean it's composite? No. You can't write 7 as a product of integers, right? So it's important that the integers are not containing 1, right? It has to be a product of non-unit integers. So r and s, where r and s are greater than 1, right? So if r and s are greater than 1, that implies that r and s are both less than n. I did. So then what's the conclusion? Then, if that's the case, r and s are integers less than n, therefore, by the induction hypothesis, they have prime factors. And if r or s has a prime factor, then of course n plus 1 also has a prime factor. Hence, P of n implies P of n plus 1, so by the principle of complete induction, we've proved that every integer, or positive integer, has a prime factor. So that was how that's done. Well, I guess I owe you guys I will have a video where I address the many mistakes I made this morning. And I should probably give you guys back your test. Yeah.
Are you going to collect the bonus homework?
Oh, I should collect the bonus homework. Yes. Thank you.